Welcome to the 4.0 Cyber Defense Defending Network module. I am Dr. Ala Jabbar Al-Maliki from the School of Computing. Every secure network requires a strict perimeter. A firewall serves as that essential first line of defense, physically or logically separating a trusted internal network from the public internet. Often, this involves creating a demilitarized zone, or DMZ. This isolated subnetwork safely exposes an organization's external-facing services, like web and email servers, while keeping the vital internal network hidden from untrusted traffic. This block diagram illustrates the core operational logic. A firewall actively evaluates incoming packets against a predefined configuration, determining exactly what traffic is accepted into the network and what is rejected. But firewall is an umbrella term. In practice, network architects must choose between four distinct paradigms: packet filtering, application gateways, circuit-level gateways, and stateful packet inspection. The choice between these models boils down to computational trade-offs. You are balancing exactly how deeply a data packet is inspected against the CPU and memory required to perform that inspection. Understanding these specific architectural differences is critical. Selecting the wrong type of firewall for your environment results in either security failures or network latency. We begin at the baseline of network defense, the packet filtering or screening firewall. This operates on a purely stateless model. It examines every incoming packet in complete isolation, with zero memory of the packets that came before it. It looks exclusively at the packet header. It quickly checks variables like packet size, protocol, source and destination IP addresses, and port numbers against a static checklist. If the header matches, the packet passes. Because it skips deep inspection of the packet's actual payload, it demands very little from your CPU. This makes packet filtering fast, easy to configure, and inexpensive. But evaluating data in a vacuum creates a vulnerability. The system is blind to larger behavioral patterns. This lack of historical context and user authentication invites exploitation. It leaves the network susceptible to coordinated strikes, like ping floods, SLIN floods, and IP spoofing. Without the ability to distinguish a malicious swarm from normal traffic, the firewall processes the rapid-fire requests until the system crashes. Relying solely on static header checks is procedurally inadequate. Evaluating packets without understanding their relationship to one another leaves networks critically vulnerable to coordinated attacks. To solve the vulnerabilities of stateless filtering, network engineers developed proxy servers, also known as gateways. The first iteration is the application gateway. Instead of reading flat headers, this intermediary program negotiates directly with the client application attempting to connect. This diagram maps how an application gateway alters traffic. It breaks the direct line of communication between the outside and the internal network. The gateway forces two separate connections, one to the proxy and a second to the destination. The internal computer remains hidden. However, this architecture requires significant resources. Forcing a firewall to negotiate and authenticate every client application consumes vast amounts of CPU and memory. This creates a unique vulnerability. Because authentication requires processing time, application gateways can be targeted by flooding attacks that aim to overwhelm the authentication queues before a connection is ever completed. The more secure alternative is the circuit-level gateway. As shown in the lower half of the diagram, the order of operations shifts. It verifies the user login ID and password first. After confirming identity, it establishes a virtual circuit, securely routing requests and masking the internal IP address. Proxy gateways offer high security by severing direct connections, but their computational cost creates a performance bottleneck. The industry required a more efficient solution. The engineering problem was clear. How do you achieve near proxy levels of security without the crushing CPU latency? The industry standard answer is stateful packet inspection, or SPI. SPI analyzes the historical context of the entire IP conversation. When a spoofed packet arrives, a basic filter passes it, but SPI rejects the threat. It uses a dynamic state table to track the TCP handshake and preceding packet sequence. The security mechanism relies on synchronization. If a packet claims to be part of an established connection, but its metadata contradicts the history in the state table, the firewall drops it. By making the firewall context-aware, SPI neutralizes IP spoofing, ping floods, and SYN floods. Because of its efficiency, stateful packet inspection is the core technology built into major network hardware, from enterprise-grade Cisco routers to home office systems. SPI represents a functional architectural balance. It leverages the history of a data stream to provide defense, while sidestepping the latency of a proxy server. A firewall's physical architecture defines its potential, but its actual performance depends entirely on the specific access control logic programmed into it. Modern enterprise networks frequently deploy hybrid firewalls, combining the virtual circuits of a gateway with stateful inspection to build overlapping layers of defense. Regardless of the hardware, traffic rules are typically managed in one of two ways. The first is blacklisting. This is a permissive model where all traffic is allowed to enter, except for specifically prohibited IP addresses or sites. The primary weakness here is logistical. Because it is impossible to list every new threat or malicious server in real time, dangerous traffic inevitably slips through. The inverse is whitelisting. Everything is blocked by default, and the gate only opens for explicitly approved entities. This relies on the security concept of implicit deny. If a packet cannot prove it belongs on the approved list, it is automatically rejected. No matter which logic you choose, an expensive firewall that is poorly configured is just as dangerous as having no firewall at all. Proper configuration requires continuous, vendor-specific training. Your logic must adapt as rapidly as the threats attempting to breach it. Mastering network defense requires matching computational resources against threat complexity. Whether you are evaluating stateless headers or tracking the history of a stateful conversation, the architecture you deploy dictates the survival of the network.